So I'm going to talk about when we're dealing with systems, especially when we're having to deal with changes a lot, and how can we deal with these types of changes as we go, somewhat trying to keep our systems clean without, with still allowing a lot of these different types of changes quickly, especially as things are changing very rapidly. And so ultimately, we want to sustain our architecture in the long run, whatever kind of architecture we may have. And I'm going to go through a set of patterns and ideas and have a little bit of some code example as well. So really the motivation on this is parts of your system are rapidly changing. We may have, for example, new rules, like maybe you have a new cell phone and we're always selling new types of services for our cell phone. They're quickly changing and we need to kind of remap this. Maybe we even have new types of products, new cell phone product comes out, and we want to sell that, or these different types of services on those cell phones. So how can we handle these different types of variabilities? Or you can even think like insurance policies. The rules are constantly changing as they learn new information, and we're having to adapt to these new types of insurance rules as the actual data becomes available. We want to calculate your risk and charge appropriately depending upon, like, if I'm 25 or older, and if I have a car or I'm a homeowner and I'm trying to calculate these, well, these are constantly types of changing and adapting things. In fact, I'm even working on, for example, right now, I can't tell you a lot about it because it's a startup and they made me sign an NDA type thing, but it's kind of what it is basically an app. It's an Android app, and we're developing, I could tell you that much, and I could tell you basically it's kind of a game with contest type things. And so constantly though we need to change and adapt that system with new types of contests and new types of variabilities within that game. And so that's varying a lot, but we don't want to like hard code that and just keep going through a lot of sprint cycles to adapt to that. So we need a quick way to be able to adapt and change to that. And so the core idea that I'm going to cover here over the next 40 minutes, I don't have enough time to go in details, and there's a lot of details you can look at, but I'll give you the big picture, is really we want to separate what changes from what doesn't. So the things that aren't changing, we can leave stable and not having to worry about it, but we have a way to inject these new types of changes into the system. And we want to protect these type of core components. And then we find these variability points, these hot spots, and sometimes we might have hook points or ways to kind of describe these changes. You'll use metadata quite often, or you'll have ways of plugging in new types of strategies as you go for dealing with this. So this is a core idea that we're going to come up with. And part of this is related, I was talking to somebody at lunch, and they noticed that I had been involved with the big ball of mud paper, and they were like, oh, do you like, that's what your passion is, writing or dealing with big balls of mud? I'm like, no, not particularly, but I mean, it's a reality. And I guess I'm best known for big balls of mud because me and Brian Foote wrote that paper a long time ago. And it's like the de facto standard. And something that Brian and I wrote is when you really get these types of architectures, if you're able to separate out things from changing from other things that don't change, separate it into these shearing layers, if things are all in the same area, something changes a lot from something it doesn't, it has a tendency to entangle or tear up the system as you're changing it. It makes it very hard to change ultimately, and you can end up with a big ball of mud. And we were highly influenced by Stuart Brand's book. It's a great book, by the way. He's got How Buildings Learn. It's great coffee table material you can put in, has great pictures in it. But it talks about how even in buildings you separate like the space where this is at, and the foundation, pretty hard to change. And even the plumbing, you're going to change much slower, but like the lighting and the electrical, you get so you can adapt that much more quickly. And even our software systems, we can think of that as very similar. So one of the things to kind of help protect your systems a little bit is to factor your system so that they change at similar rates. And this is nothing new, obviously. It's been around a long time. This is an old good design principle, and even layering is a good idea with this. But you even think from software systems, things like the infrastructure or your schema. Schema is easy to change. The problem is once you get data in it, and I've been part of a lot of large systems, all of a sudden they become much harder to change because a lot of other systems become dependent upon what that schema is and what the data is. We all know we can change it very easily, but once you get the database going, and it's kind of described there, Obviously, code is data, and then we compile it, right? We type in the Java code, have our functions or our algorithms. And ultimately, things in a database, as long as the database isn't changing, we can always put new values in a database, including even metadata or some description of what's going on. And so obviously the things you can change at the bottom in most systems, you can change much faster. It's not that we can't change the others, it's just that generally once you've chosen a platform and an infrastructure and stuff and you've kind of started settling on the schema, they change much slower than the code or the data itself. And so when Brian Foote were writing this, and it was like, okay, if you have a big ball of mud, something really messy, how can you make it so that you can change the other part of the system and keep this clean? And in fact, Michael Feathers even talks about this with working effectively with legacy code, is really if you have a piece of legacy, what you do is you try to wrap it up. And so that way you give it a facade, use some well-known design patterns, things that you can give it a pretty interface, and therefore your new parts of your system, you can write much cleaner and change it and adapt it much easily without just adding to the mud. And that's the big thing. It's almost like the Boy Scout model. In the US, we have the concept of a Boy Scout. If you ever go to the campground, you never leave the campground any worse than what it was when you were there. In fact, usually if there's a little bit of a mess next to where you camped, you're taught to go ahead and pick up that garbage too. And so the same thing with legacy. We're not going to make the legacy worse. So if you do have a little bit of a mess, but you're writing new systems and you're having some variability, one good kind of pattern is you can use things like adapters and facades and decorators and other types of things, leaving the core part alone, and therefore evolving the system more cleanly and inject the adaptability rather than just add to the mess. But ultimately, what we'd prefer is not to even have a mess, even though it's hard to completely get rid of all entanglements, but I mean, that would be the big goal. So something that Rebecca and Worthbrock and I have been working on lately is a lot about sustaining architecture. So these first set of patterns are just good things to do, regardless if you're dealing with variability or not. But as your system evolves, is sometimes, like Eric Evans talks about this as anti-corruption layer, but you can put a rug at the front door. So you have a nice component, or a set of components, a nice API. People have been working on this, and so now you have these new requirements. Maybe a new client you're taking on. And the new client is kind of like your old clients, but they always have their little twists on things. And this component's fairly clean for handling things, and so you want to handle this data variability without messing up the core component. Because if every time you have a new client, you have to go in and just add if statements or cases or all these one-offs, things can start getting kind of messy. So what you can do is what we call put a rug at the front door, wipe your feet before you come in, so that the internal component's kept clean, and maybe you have to do a translation or filtering or cleansing or two-way adapters, and let that be where a little bit of the mess is, but it protects your internal components. And so, for example, when you wipe, we talk about encapsulate and ignore, you might have some protected pieces here, and they're working real well, but you have a lot of external clients. And you really want to be able to do collaborations and make sure everything works well and handle all these other things. Well, what we can do is by wiping your feet at the front door, all these different client systems may have their own way of looking at things, a little bit of a unique way. And what we can do is come in and kind of map it. Sometimes you're going to have to do some translations, write some different types of filterings or cleansing things. And then we can call into our protected components, keeping everything clean. So as you're going through, you're coming in, and maybe you have to do some custom validation for the customer. And so this way you can still have all your one-offs. But the nice thing is you can handle a new type of requirement more quickly without having to go in and handle a messy thing here. Because if we keep embedding all these different variations into our protected core components, well, pretty soon we're starting to bring a lot of mess in, and it's not so protected anymore. And we'll have to handle a lot of different case statements, and even testing and maintaining the thing can become pretty complicated. Where if it's kind of behind in a protected area, you can really move forward and keep things kind of filtered from that. Now, so those are some of the core ideas that we worked with when we were dealing with these types of variability. However, things are changing rapidly nowadays. You know, we're no longer in the age of we're just desktop computers. You know, I remember when I was first beginning programming, it was desktops, you know, and then we had the internet and the web, you know, and we had more personal computings coming up. But nowadays, you know, we're living in the app world. Things are changing rapidly, and cloud computing, and there might be a lot of services, and I want to reuse and plug different things together that originally were never meant to work together. And in fact, the perspective of, I like to think of, I mean, some people call this ubiquitous computing. They're almost like it's everywhere. But ubiquitous is almost apparent. Sometimes there's stuff going on that we don't even see. So I like ambient light. It's all around us, but a lot of times we're not even aware of it. And so things are really changing from what's going on at a much higher rate, and we need to much more quickly adapt. Even businesses need to very quickly adapt to remain competitive. They have to very quickly adapt to these changing environments and not have to go through the normal months to release or whatever. They have to be able to release within weeks, if not days, sometimes, to handle new requirements. So how can we deal with that? How can we even extend this? So some of the core ideas is we're going to protect components. We can write new components. We can still write Java code, you know, and what I was talking about before, and we can still write these little one-offs to kind of interface with this, and that can help us a lot. We can get some big wins, but ultimately we have to handle this much quicker. And this is actually a picture of me in the 90s, but in my youth, my misspent youth, there was two bad words, the M and the R word. And I don't mean marriage or in relationships, you know. What I mean is metadata and reflection, or meta and reflection. I liked it. I was passionate about it in the 90s. But it was not that accepted at that point because it was considered, you know, dangerous, too slow, all these other types of things. You know, Java was just starting at that time, and things have evolved a lot since then. You know, we've really kind of come into a new era where metadata and reflection is becoming accepted. In fact, most of you are using it all the time, even if some of you may not even realize you're using it. Sometimes if you're using JUnit, you put annotations on at test. You're using metadata, right? And there's some reflection going on and other things under the hood. You know, we're using all these frameworks with XML type things. And so it's become definitely, this is kind of the error of the new way that in order to really move forward, we've had to kind of go this way, which makes me excited. I was looking for it back in the 90s, but now it's kind of an exciting era in computer science and where our applications are going. The problem with metadata depends on whose perspective or who you talk to with what it means, right? So, you know, some people, depending on which standards committee or anything else, and so metadata can be very confusing. In fact, I've had this issue before. I remember once when I was back in the 90s when I was working, I was doing research. I was working with Ralph Johnson, and then with Caterpillar Inc. was funding the big earth-moving equipment company, was funding my research, and they were very interested in metadata. Just for well, they weren't. They were interested in their systems being able to change more quickly, because something as simple as part number inside Caterpillar, they spent millions of dollars when they bought a new company, and they had to adapt their systems for something as simple as part number. Now part number has to go from 10-digit with all these alphanumeric rules and other things and validations to 12 digits with some kind of new rules. And you could spend millions of dollars updating their system with many people hours, you know, taking a long time. You know, so they were involved in funding research at the University of Illinois at the time. And so I would go talk to these Caterpillar managers, and I would be talking about, well, you could have, you know, metadata for part numbers and metadata for metadata, and they'd start scratching their head and get blurry-eyed and, you know, like, what are you talking about, meta, the meta? Because it can become very confusing. In fact, and so what I did was I emailed Ralph at the time, and he gave me, this is back up from an email quote I'd gotten from Ralph, is, how can I explain to these Caterpillar managers and other people, these technical people, about metadata? And so this was kind of a nice little a simple description. And what Ralph had sent me an email back, it says, if something's going to vary in a predictable way, store that description of the variation in a database so it's easy to change. So then it's like, oh, so what we're going to do, Mr. Caterpillar Manager, we're going to store information about your part numbers in a database. And the part number will have descriptive information about part number. It's a metadata about part numbers. And it'll talk about the rules and the variations, how long it needs to be, and things like that. And so that made things a lot cleaner and easier to talk to these people, and from understanding that. And even though so that kind of simplified the concept from their perspective, but it was really kind of just focusing right in on something they understood. Now, I claim anything you can do, I can do meta, and that's very true. But there's also meta can be beta, right? It might be better stuff, right? But it might be beta too. Just because you can do something with metadata doesn't mean you should. And that's where I want to make sure I don't oversell it. I get excited about this, but there's trade-offs. When should you do it versus when you should not do it? I mean, here's another way of thinking about metadata. It's just data about data. For example, we might want some data about books. Here's a book that some of us have heard about before, the Design Patterns book by the authors Gamma, Vlasides, Johnson, and Helm, published. And so this isn't the book itself. It's data about the book. It's describing the book that can be used, and there could be other data that's got all the chapters and things like that, the actual data associated. But this is the descriptive information from that. Now, usually when you're dealing with metadata, you can break it down from 3 perspectives. And Brian Foote, a colleague of mine, did a talk a few years ago. He talked about metadata, the good, the bad, the ugly. Very interesting talk. But really, you can kind of break metadata down into these 3 perspectives, whether it's manifest, markup, or meta objects. And fortunately, I mean, there is a good and a bad. Sometimes it can be ugly, right? Even dealing, I mean, I don't know if sometimes you've opened up some XML type stuff and tried to parse it. Fortunately, sometimes we have some nice parsers to make it more readable. But the markup, we're really just trying to describe things. And in fact, we see this all the time. We have annotations in Java and other languages. We have ways of describing these types of things. And in fact, with JUnit, there's your list of JUnit annotations. Most of us have used these different types of annotations if you've ever used JUnit at one time or the other. And it's just some metadata that you can use associating with that. Sometimes you want custom metadata for dealing with these types of things. Fortunately, and sometimes meta object is when you really go the next level. You're creating a meta architecture layer. Fortunately, most of the time, we don't have to deal with that. Most of the time, just a little bit of markup and the manifest, having a little bit of annotations and stuff, it's good for most of what you need for handling these types of flexible things. For example, you may have an online store catalog, and we're selling new types of things. And now you give me some new product you want me to sell in my catalog, and I can have a way of describing what the structure of that is, and I can use that at runtime for doing that without having to hard code this whole new system in. I can interpret that and have this descriptive way of reading what kind of attributes, what kind of values it should hold. For example, canoes have length and width, whereas sweaters have sizes like small, medium, large, and extra large in the US, for example. But ultimately, when you're dealing with custom metadata, it can vary a lot. And there's this very good code, there's a lot of code examples. I've done a lot of work on these adaptive object models. That becomes very flexible systems. But if you go to codeproject.com, there's a lot of examples, including Java, C#, other languages, C++ even, of implementing some of these different types of AOM type systems. I don't have time here, obviously, to go into it, but you can really go the next level with this. So that's metadata. So metadata gives us really just ways of describing some of our variations. It can become very powerful and we can push it all the way, but most of the time we just need to describe some simple variations. So this client, these 2 clients are very similar, but they call things differently. And they come from different sources and we need to map it. So we can use some XML or some kind of other mapping metadata to say how it maps to the way that we're going to process things. And occasionally we may have to translate things. So another pattern that you can use for when you have to handle these variations, so these 2 systems are very similar, but they have a little bit of variances, maybe different business rules. How I have to validate your business rules from one client, so you're giving me maybe some insurance information, and then you want me to send letters to all these customers, and you may have different rules about how I have to process that, whereas my other client, another insurance company, they're similar, but they have different rules. So I want to plug those in. Well, you can use a well-known pattern that we've written up called dynamic hook points, where you can have well-defined hook points in your code where you can dynamically plug in a new Java implementation or whatever you want. You can have a new strategy. It's like a dynamic strategy that you're saying, oh, when you're on this client, you look up some information based upon some metadata, and it says apply this business rule, and you go find maybe you're using reflection, and you can actually implement and bring in this new piece of code at runtime. And so this is very powerful. I've used this quite a few times. For example, with this, we had a custom invoice program that we had that all our clients would have service level agreements. But depending upon the service level agreement, they'd all have a different kind of variation about how we're going to bill them and things like that. So whenever we had a new type of client, we could have a little custom hook, a new rule, and we can write those custom rules without having to go change all our core systems. We just had a place where we can all of a sudden plug in your new type of rule very quickly. And finally, the last pattern I want to go over, and then I'll go over an example, is what we call paving over the wagon trail. So if you have something that you're seeing as you're writing, every time you get a new client or a new requirement, you're constantly having to do something very similar. Maybe there's minor variations, how it maps to the database, or, you know, the GUIs are very similar but a little bit different, but you're repeating that task. And sometimes the code's almost being repeated, and you're trying to find the abstraction. What you can do is you can find a way to make that easier, streamline that. Sometimes this is just as simple as having a template or a script that somebody comes in, here's the default template, you just fill in the values, and voila, you make it easier for your team to write this new type of thing that's going up there. Other times what you do, and you see like GUI generators doing this, is they have ways of generating from some descriptive language some ugly stuff that you never have to look at, but it's handling all that. So you may even have a framework or whatever that does that or generates code. Ultimately, you can really push it to the point where you're even writing more of a DSL, a little bit of a mini language for handling some of those variations. Now, when you're hitting a DSL, obviously that can become much more complex with what you're doing with this. And we have lots of examples with people that's built a lot of tools for this. I just do want to at least step back a little bit, because when you start getting to this point, you're really starting to push the level of your flexibility to that next level. You're really kind of making things really meta. I mean, because our traditional programming, what we're doing is we have our series of steps with conditionals, and we're handling things of, you know, every time we have a new requirement, we're writing some kind of new piece of Java code or whatever for managing that. However, sometimes what we want to do is we want to have a way of describing those types of changes. So when we have a new client, here's how you calculate an insurance policy. We want to put that declarative information out into a database so we can interpret and realize that much more quickly. And in fact, Martin Feller and Rebecca Parsons has written a book about this recently, and usually what they focus on is, and what's most in their book, is they have this DSL script that you parse with a semantic model, and ultimately you might even generate your Java code from this, though that's not necessary. That's very optional. And in fact, a lot of times, I mean, your DSL can be something that you're actually just even interpreting those types of rules without, the Java code itself is actually interpreting that. So that's part of your architecture. It becomes, in a sense, a higher level meta architecture from that. So let me jump into an example on this. We have enough time, and then I'll leave plenty of time for questions for this, is how can we deal with client variability? And I'll give you an example that I worked with for a company out in Silicon Valley a few years ago. I had a team of developers, and we developed a system for this. And this was for importing orders. And we also imported a lot of other types of things. But from the simplest perspective, what happens was we really wanted to have, we had this standard format for imports. The problem is a lot of the clients, some of them had They wanted to give us all their orders through mainframe systems, or CSV files, Excel spreadsheets, or tag delimited. They had all these varying formats. You know, sometimes they would do what we wanted. They'd have a nice XML format of exactly what they wanted, and they would even map to the way we were mapping it. Because we would tell them ahead of time, and they would have their developers write a system that would export it right to what we wanted. But unfortunately, sometimes to do business with these people, we had to really be able to adapt. Plus, we were more agile and lighter weight. We could usually bring a new client on quicker than if they had to get, you know, a large company sometimes moves slow. And so by the time we'd be able to get them to write something, we could have already had it implemented. But the problem is we had literally hundreds and hundreds of these little one-off little import order things that we're trying to manage and maintain. So it became a maintenance nightmare. And then if something changed to our core system, then and if we needed to change the database, we'd have to go change a lot of these systems. And so we'd have a lot of these specific rules in these self-contained import programs, but it made things very complicated. So basically what's going on is client has some kind of order or whatever, and they might email or FTP, or there might be some kind of service that they're talking with, and they had all different kinds of ways they wanted to give it to us, depending on the client we had. And then we received it, we wanted to process it, and ultimately go into our place order part of our system. So what we ended up doing is, this is kind of too many details on this, so don't worry about the picture too much, but it's really talking about, we had all these different services, ways of gathering, bringing this in. So we had this gathering thing, so it was generic. It had different ways of describing the ways that you wanted to give it to us. And we can use kind of a little metadata to say, go get it this way, and here's the security credentials, and we can handle things like that. And then once we brought it in, what we did, because we wanted this to stay clean, the place order part. This was the way that we wanted to look at orders and process things cleanly. And we had a lot of different ways of dynamic rules for doing this. But what we would do is we'd bring this in, we'd transform whatever they gave us to map it to ours, which sometimes took data and had to split it or apply real weird rules or whatever. So we'd do a lot of transformation, renaming things, mapping things. And then we would validate it. Sometimes we had our own validation rules with metadata we could just look up and order. But sometimes they'd have a custom one, so we could use that dynamic hooks patterns to plug that in. And then ultimately process it. And then we even had a little bit of a way of, they wanted different ways of acknowledging things. And so we had a little bit of a descriptive language for that. But the nice thing of what we had here when we were working with this system is when we had a new client now, we could very quickly, within a few hours, most of the time, sometimes within a few days, depending on what's going on, and if we had to write a little bit of code for it. But a lot of times, if depending on what they gave us, we already had some metadata descriptions that say, oh, if it's a tag delimiter file, here's how, you know, this part maps to what we have. And if it was a clean mapping and we didn't have to write any code, we could just describe in metadata what the mapping was. And if we already had the validation business rules, they didn't have any weird validation rules, things that we hadn't handled before, one-offs type things, we could very quickly bring that up. The worst case is sometimes they may have some very weird way where they'd have, you know, like maybe it's from a mainframe and they're saying from column 1 to column 10 is first name and last name. Then we have to know the rules about how to split it, so we'd have to write a little bit of a piece of custom code for handling those types of things. Whoops. And then occasionally we'd have to write a one-off validation rules. But the nice thing is, because we were using the dynamic hooks pattern, which is happening here, is even in our validation rules, we had ways of dynamic. This is actually in C#, because they were actually doing C#, but you can do the same thing, you know, in Java for tagging your functions. We had ways of plugging in new types of functions and even storing in the database or new types of rules that kind of mapped into ours. Something that we had that was going on here when we were running this, this is an example of the dynamic hooks pattern that I talked about, is in this part, as long as we had a common interface, and then if we needed some kind of values to handle that custom new piece, so that way we can write a new piece of Java code very quickly if they had weird rules or new rules that we haven't handled yet. But we had a common context that had ways of getting access to any of the data values or looking up things from the database, so we could pass in that shared, that common context, whatever, and then we could write whatever new Java code But then it kept our core system stayed the same. So it was real easy to process and build in a new business rule, just using a little bit of metadata and having a way of linking in this new function that we'd write for that. So it's very powerful for what we were doing. Now, I want to end with a few minutes and then leave some time for questions. Is talking about some of the architectural practices when you're supporting data variability. And so the core principle I talked about early on, and I gave some very high-level patterns of things to do, is we're trying to separate the parts of the system that changes a lot from the parts that aren't changing a lot. That way, when we have new change, if it's separated, any change to the parts, the system that needs to change a lot will not mess up, the stable parts of the system. Well, that's just good design principles we learned, a long time ago, so we still want to apply that here. And then we want to learn. So a lot of times, I don't know what part of the system is going to change. So as I'm evolving the system, and we're constantly, even if we're being agile and we're doing sprints and we're going through every few weeks and we get these new requirements, I'm starting to learn and adapt and say, oh, this part of the system's changing more than that part. So it's important to learn and refactor and redesign as we go and keep that clean and separate things out. And so that's back to the minimize that architectural debt or technical debt, as Ward Cunningham named the term a long time ago, is really trying to keep things from getting too messy and watching for that is. And then if we see parts of the system that's difficult or time-consuming, we can really create a way to make that easier, whether we use a little bit of descriptive data, some metadata, or maybe we create templates or some ways for automating that part of it. Maybe even ultimately it pays off sometimes to even write a little bit of a DSL for handling that. And most importantly, which I think one of the problems I've seen with a lot of the Agile community, they always say, wait until the last responsible moment. Well, what's the last responsible moment? The last responsible moment could be before I go out, and it's going to cause a lot of churn and a lot of technical debt to put that in. So even though I can do it, it can cause a lot of problems. Something that I've been really trying to push here with the Agile community recently is sometimes there's a more responsible moment. It's still okay to think if you're doing Agile. You don't wait until the end to do security, or all of a sudden we're going to check reliability or performance. If we know we're going to have to scale up, we don't want to do it too early, but there might be, after a few sprints, we say that's the time that we need to that's a more responsible time that we can start dealing with that, and that can influence your architecture decisions. And it's okay, and you can learn and evolve from that as we're going. So as you're sustaining your architecture, it's really important to kind of follow through, and it still takes a lot of work. But don't ignore the little things and learn as we go. And so these have been some good principles for sustaining the architecture. Don't let it just sometimes it's like, okay, we're being agile, just let the architecture magically emerge. Well, for little stuff, sometimes that works. But if you're really, dealing with things and we're learning and adapting, it's okay to still kind of think and do responsible things at the right time to be able to adapt our systems. It's still okay to do framework sometimes, even if you're being agile, you're doing Scrum. It's just, the main thing is don't overthink it, balance it. So there are some indicators that if you've paid enough attention to your architecture. For example, if your architecture is clean, generally people won't be paranoid to go work on part of it. No developer wants to work on that part of it because they're afraid they'll break it if they touch it. So if you ever have part of the system everybody's paranoid about touching, you've got a little bit of a problem. So you know that things have kind of evolved and you made it so you can handle some variability if developers can really add these new functionality more easily. And you're able to incrementally bring this in. It doesn't mean that sometimes things don't break. It doesn't mean that some parts of the system aren't complex. It just means that you've separated things out so that when you do have these types of variabilities, you're able to more cleanly put that in and separate out those types of variability without affecting the whole system and worried about breaking everything. There's also some other things that you can do, and this is a paper I wrote with these two Brazilian guys, Eduardo Gerhard, he's an interesting character, fun guy, and this is Paulo Merson. And he actually works at basically the central bank of Brazil. So there, it's highly regulated industry, and a lot, but even they're doing a lot of this. They're trying to become more agile, even though it's hard for large government organizations to be that flexible. But sometimes as you're going, you want to make sure your architecture stays clean. There's some good ways that can help you with this, such as some continuous inspection. Watch things. In Java, fortunately, and he has some open source Java tools that we mentioned in our paper called continuous inspection. And if anybody interested, just email me and I'll give you a copy of this paper, but you could probably find it online if you Google for continuous inspection and my name or something. But it's really you have ways of looking at things. So for example, you may not be able to automate all of it, so you're constantly kind of watching what's going on, and you're inspecting things. And sometimes you can even have Java tools, for example, before you check things in, you're kind of looking, are people using the architecture correctly? Or maybe we have a problem with our architecture and we need to evolve it because developers are always having to move around and hack around what we have. So there are some techniques that you can do. Obviously, we know about the typical ones, the code smell, but you might have some other ones that you can write, and there's some open source tools that let you actually write your own little scripts for architectural conformance. Make sure people are using the persistent layer properly so that we don't get SQL injection and that we don't have any passwords open, for example. And you automate where you can. So, as far as some design values for supporting variability, it's important to respect your sharing layers, understand what changes. But I always like to end on this. Don't over-design. The problem with a lot of these systems, most people I know that's written these highly flexible systems, it's like the coolest thing we've ever done. And they like to show off with everybody and show all their other developers. It's like, oh, look at how cool this meta architecture and what it can do is. But sometimes, I mean, like I said earlier, anything you can do, I can do meta. And that's true. But sometimes that makes things more confusing and hard to maintain and follow through. There might even be performance issues. So you should only put this in when and where you need it. And so I have a lot of resources, and I wanted to make sure to leave at least 5 minutes or so for questions or discussions or challenges or however anybody wants to put it. So anyway, that's what I have. So, dziękuję. Thank you very much.